So hello everyone, welcome to lecture 17 on the finite element method. As always, we have a short summary of what we have done so far. This is the map of the finite element method that we wanted to look into. And for now, we are dealing with one-dimensional finite element method. We talked about different sources of approximations in the finite element method. And we also mentioned that the strong form that we begin with is a differential equation, the second order differential equation that you can multiply with a test function and integrate over the domain to come to this so-called weak form. And then based on this, let's say, understanding, we had a more detailed map of what we want to do. Again, the starting point is a second order differential equation. That's a strong form. And in the case of 1D FEM, it looks like that. Then you multiply by test function, you integrate it, you come to the weak form. Then you discretize that, so you come to a piecewise weak form. Then we approximate that using, let's say, shape functions, and eventually you integrate it, you come to your stiffness. And then once you have your element stiffness, what you need to do is to assemble those stiffnesses and get your global stiffness. And then if you remember, this assembly process is basically the opposite of that discretization step that we did at the beginning. And the course started with assembly process anyway, so you are all now experts in assembly process. There is nothing new for you there. So you want to understand the stiffness for one single element. Then we learned this concept or this topic of shape functions or hat functions or tent functions. These are very powerful tools to allow us to approximate the domain or displacements in this case, or the test functions, and that is the way you are going to approximate them. And the test functions, they have, not test functions, sorry, the tent functions, they have this property that, let's say, n1 would be 1 at node 1 and 0 at every other node, so all the other nodes. And if you have a linear approximation, you have 2 of these nodes. If you have quadratic approximation, you have 3. If you have cubic, for instance, you have 4 of them. And we looked into a lot of these shape functions, let's say linear shape functions, quadratic shape functions, and cubic shape functions in 1D. Then based on what we had learned using these shape functions, we looked into this problem. Now, this is your strong form. And for this particular problem, you have the analytical solution to keep as a benchmark. And using the shape functions or hat functions, we calculated the approximate solution for one-piece linear, two-piece linear, and one-piece quadratic. If you remember, for one-piece linear, basically you get that line, which would look like a line connecting the 2 points. And then for two-piece linear, you would essentially have 2 little elements. And if you also did quadratic one, you hit exactly the analytical solution, okay? So again, the message here is that if your approximation space is rich enough, you can cover the analytical solution. Now, to give you a feeling of what that weak form means, we also started interpreting what, let's say, the meaning of the differential equation is in its weak form sense. And we realized that these terms on the right-hand side, they are basically the forces. They are the forces at nodes. And then we also discussed this many times, that if you have a truss structure, you apply the forces at nodes. So there is nothing, let's say, limiting in that sense about this. But we also mentioned that if you have a uniform load through the elements, it doesn't have to be uniform, by the way, but if you have, let's say, body forces through the element, we can also include them using this integral. For now, I omit that, but we will come to that shortly. Okay, so the corresponding weak form would look like this, and now here you have basically forces. And the next thing we wanted to do is to look into, let's say, the left-hand side, and we realized that all of that could be cast into, let's say, this format where you have a stiffness, and if you have a linear element, you have a 2x2 stiffness, and the terms of the stiffness, they look like this. If you have a quadratic element, you have a 3x3 stiffness, and then again, the terms of that stiffness, they look like that. And eventually, if you unify everything, you come to this picture. So you will have a stiffness matrix that it is looking like EA times something, and that Kij can be understood as this just one function. And then again, if it is quadratic, of course, this is the same thing, or if it is linear, this is the same thing. But now that we have this, so we know that the problem, let's say, from that differential equation, we have come to a single stiffness matrix. And from that stiffness matrix, we have come to the components of the stiffness matrix. So all you need to do is to do the integration. So for that integration, we learned, let's say, Gauss quadrature or this quadrature rule. The idea was that if you have a polynomial, you can always integrate that polynomial by evaluating the value of the functions or evaluating the functions at a point in the domain times some sort of weighting. Now, if the function is linear, it turns out that that weighting is basically the length of the domain, and that point, that magic point or quadrature point or Gauss point, is exactly the point in the middle. If this is a linear function, this is exact. Okay, so this is a very interesting and powerful tool. And then the question is, what if we want higher order polynomials? Now, if you want to talk about higher order polynomials, we said, well, this would have too much complexity. So why don't we just limit ourselves within a domain of -1 to 1? And then after we learn the approximation, after we learn the integration, we will make a mapping between the two. So that seems like a, let's say, a smart way of dealing with this. And that's exactly what we do. So now you assume that you have a quadratic function, for instance, from -1 to 1. And if you want to integrate it, you can again see, you can just have evaluation of that functions at two specific points, and that gives you an exact integral. And then based on this observation, we collected what we had for the linear and quadratic case. I told you what is that for cubic, and you can prove it. And basically, that brings us to this one slide on numerical integration using quadrature rule or Gauss points. And basically, what it tells you is that if you have an integral of a function of a polynomial, again, I mentioned this is a polynomial, it's not just any function, but it turns out that for our purpose, for the finite element method, the way we do it, polynomials are everything that we deal with anyway. So this is not a limitation for us from that perspective, at least. Okay, so the integral of a polynomial is a summation over some evaluation of that polynomial at specific points that are Gauss points times some weighting factors, and then we had that for linear, quadratic, cubic, fourth order, and fifth order polynomials. Okay, now that we have that, we come back to that other question of how to integrate that integral from A to B. And we learned that in order to do that, all you have to do is to find a mapping, a transformation between your AB domain to -1, 1 domain, okay, which is shown here. So this is the mapping. Now, this domain from A to B, this is your X space. This is your physical space, and the domain from -1 to 1, that is the natural space. So in order to calculate that mapping, you need this this thing called Jacobian. So basically, Jacobian is the thing that does the mapping for you. And once you have that, then you can integrate that thing easily. So basically, instead of integral from A to B, you would have an integral which would look from -1 to 1, and then some function of C times, of course, that, let's say, J itself, that Jacobian itself. So I think there is a little typo here also. This should be the Kissy, of course. Okay. So that's that. Now that we know that, we want to just test it for a few examples. So we did this example together. We said, well, the example is this. So let's integrate that using a linear approximation. And when you do that, you see that the linear approximation gives you, or that Gauss point evaluation for a linear approximation, that gives you 24 for the integral, but also because it's a simple integral, you can calculate that exactly, and it's also 24. So again, we recovered exactly what we expected, and it was perfectly fine. So what we want to do today is to do a few more examples of this to understand the meaning of that J also better. So we want to better understand numerical integration, and we want to better understand what J, that Jacobian, that mapping means. And when is it a constant, when is it not a constant, and what are the implications of that. Before that, I just show you a few slides, basically. So it's sort of a finite element library in 1D. We would like to name elements if you want, or to abbreviate them. So here you see there is this D1. So that means it's one dimensional. So the dimension is 1. And then there is CU. So this stands for a curve element. So in a 1D, let's say a line element looks like a curve. Again, if it is just 2 points, it's a simple line. But if it is 3 points or more, these are basically curves. And then you have the number of nodes on that curve. Okay. Again, for now, even if we have 3 points, we are always thinking about this. But in general, the elements that we have, they are also equally useful if you had something like that. So that's why we don't call them lines, we call them actually curves. Okay, and then they could have 2 nodes, 3 nodes that we just discussed. So that would be linear, quadratic, cubic, if it is 2, 3, 4 nodes. But then they could also have more nodes, and we can extend that quadrature rule. So I want to show you how it works. So if you have 2 nodes, basically, and everything is in the natural space, by the way. When you talk about, let's say, a finite element library, now everything is in the natural space. Okay, so this is important, that now we are always in that space of C, which goes from -1 to 1. All right, now if you have a linear element, so 2-noded element, nodes 1 and 2 are here, the coordinates of the nodes are given, and then the shape functions for them, and also their derivatives with respect to C are given. If you have 3 nodes, now this is how it looks. So you have the nodes here with their coordinates given, and then these are the shape functions, and these are the derivatives of the shape functions. If you have a cubic one, so you have four points, this is how they look. And as I said, you can just play this game. You can increase this game, so that would be now 5 points. This would be 6 points, and this would be, for instance, 7 points. You can just keep playing this game and calculate these shape functions. It's a nice exercise, but also if you actually want to test it, you can imagine that by increasing the number of nodes, or by increasing the order of your element, you will get better and better results, as we have seen before. So then there is this thing that we call Gauss points. So instead of an integral like this, we mentioned you can always have a summation over, let's say, the Gauss points. And then this one, we simply called it Gauss per element, I think, in the slides and also in the code that you write. Now, this thing also, again, if you have one Gauss point or one point quadrature rule, this is the coordinate, this is the weight. If you have a 2-point quadrature rule, these 2 are the points, these are the weights. If you have a 3-point quadrature rule now, these are the points and coordinates. You can have, I don't know, 4 points, 5 points, 6 points quadrature rules, or I don't know, 7 points quadrature rules. So these are the coordinates and weighting for those. There is really no limit, no end to this. It's a systematic thing. I don't have time to teach you how to calculate these coordinates and weights. For you, you just use them, but we also showed how to calculate them for a linear and quadratic function. But for higher order polynomials, it's also following the same strategy. Okay, so this is basically the functions. But then I want to come back to that point that I mentioned previously, that if you have an element and you have a force that is uniformly distributed throughout that element, remember that body force density that we assumed it was 0. So we want to think, if it is not 0, how would we distribute those points, those forces at points? So let's say you have a bar here, and it is under its own weight. So it's like a constant density or force density. So if you have 2 points, you may imagine that if the weight of that thing is W, you just give half of the weight to each point. Okay, that makes just perfect sense. And by the way, that would be the result of this integral. Okay, so if you want to calculate those weightings, you can exactly calculate them like this. And if you do that, you naturally get 1/2 if you have 2 nodes. If you have 3 nodes, it turns out that you would have 1/6, 1/6, or let's say if it is the weight of the thing, W/6, W/6, and 4W/6. So these would be the weightings. And the summation of them is obviously always 1, right? So all of them together, they recover the whole weight of the structure. Now, if you have more points, you keep doing the same thing. So you need to calculate what would be a correct distribution of those points over on those forces over points, so that you recover the uniform distribution, right? Okay, this is completely extra material. So you never need this. You never need this for this course. Possibly you never need this in your engineering life either, at least in 1D. But this is something that can be done, let's say, mathematically speaking. All right, so we are done with this. I just want to show you one example, actually 2 examples, but one larger one and one smaller one, to understand this numerical integration a little better, but also to understand what is the meaning of that Jacobian. Okay, so this is the example we want to be looking into. You have a polynomial that you want to integrate. It's a quadratic polynomial. So if you remember, for a quadratic polynomial, the quadrature rule that we had was a 2-point quadrature rule. Okay, but you shouldn't be fooled by that. That is really the message I want to tell you here. That the polynomial that you see here is in X space. Okay, this should not fool you that you need 2 points because it is quadratic. You need to do a transformation to Xi space, and then based on the order of the Xi space, or based on the integration in the Xi space, in the natural space, then you can decide on the number of Gauss quadrature points. Okay, that is really the key message here, that this is quadratic this is a quadratic polynomial. But the number of Gauss points that you need is dependent on polynomial order in natural coordinates, or let's say in Xi domain. Okay, so it's quadratic polynomial in X domain. Okay, so that is really the key message I want to convey through this example, and we do it by going through these steps, through the steps that this one has. Okay, so let's see. The first thing the example asks you to do is to do this analytically, and then after doing it analytically, it asks you to do it approximately using a linear approximation. So for a linear approximation, we use these. So I keep these shape functions on the side so that you can always look into it. And then we want to do also quadratic approximations, but then for the quadratic ones, we do a uniform and a non-uniform one. These are shown here. So if it is a linear approximation, see in the physical space, that is the green one, you have the 2 points A and B, which in this case, by the way, these are 2 and 5. So if you think of coordinates, this coordinate would be 2, this coordinate would be 5. Here, this would be 2, this would be 5, and if it is uniform, the point in the center would be 3.5. Now, if we want to make it more interesting, so we want to make it non-uniform, let's push that point a little bit to the side and call it 4. Okay, so maybe at point 4, we want to do that. Now, again, the message here is to have an exercise to learn this, but you should see that in the natural coordinates here down, the nodes are always uniformly distributed. Also, this was what I showed you in many different functions that I showed here. The nodes are always uniformly distributed or equally spaced. Okay, that is the natural coordinates. That's the nice coordinate system. But in the physical coordinate system, this is not necessarily the case. Okay, so that is something I want to discuss first. Why is that? So let's say in natural coordinates or natural space is, let's say generally, so almost every time that you see one, is, let's say it's uniformly discretized. Okay, this is not a very good way of wording, but it's okay. So it's uniformly discretized. What does that mean? That means, for instance, if you have this Xi domain, and if you have a third point, the third point is always in the center. Okay, so these are the nodes in the natural space. Now, this is not the case for physical space. Let's say necessary. Now, if I want to draw it, for instance, I can draw the same domain almost, and this could be node 1, this could be node 3, but if it is, let's say, the X space, maybe node 2 would be here. So what does that mean? Let's say if you compare this, so I'm going to compare this. This is one example. This is the natural space example, which is a good one. And then let's think of also another X space example. I use, let's say, orange to show it's the, X space. Okay, so if you think about the first case and compare it with the second case, maybe you can imagine what is the difference between them, or what is the complexity here. Remember, we said the mapping between the two is basically the Jacobian. Okay, so you always have this Jacobian which connects the two domains. So let's say I mean, you usually have this thing that you write x as a function of c, right? So the mapping that allows you to do that, that is your Jacobian, if you want. So you can say this is maybe something like this. And this thing, this is the mapping that I'm talking about. So this is your Jacobian. Okay, so look, your Jacobian looks here, looks like this. Here looks like that. Okay, if you want to think of like a mapping. Now, you can imagine that if you have the first one, this point comes here, this point comes there, this point comes there. The Jacobian is constant in the first case. Okay, because let's say this half portion of the domain up here would be also transformed to half portion of the domain. Okay, remember this Jacobian is basically the weighting between a length in the physical space and the length or the corresponding length in the natural space. All right, so in the natural space, if I don't know, if here you remember that in the natural space it starts from -1 to 1. So if this domain is 1 here, and if this domain is 1, and let's say in our previous example in particular, this was 2, this was 5, and this was 3.5, right? So now this would be 1.5. This would be 1.5. Okay, so you can see that here the mapping would be 1.5, but also here the mapping would be 1.5. Okay, so that scaling, that Jacobian is 1.5, it's uniform. But in the second case, if you now think about that one, so let's say this was maybe 2, this was 4, and this was 5. Now this is 1, and this other one is 2. Okay, now in the left hand side, the Jacobian is 2. Here on the right hand side, the Jacobian is 1. Okay, so the Jacobian from left and right, it changes. And by the way, it is not a point-wise, so it's not just one piece, right? It's about dx dx, but I am assuming dx is very large, which is not correct. But what I'm trying to tell you this, or to tell you by this, is that in the first case, J is uniform. In the second case, J is a function of C, so is no longer uniform. Okay, so why is that important? Why do I keep saying this to you? The reason is that, remember, we had this integral from a to b f of x dx, and we said that basically using this Jacobian thing, right? This is exactly what happens. We would say it's from -1 to 1, and now you would have that function, because x is a function of, let me even put f here for you. Okay, so this would be f, which is now a function of c, by the way, but the x would be j dx. Okay, now if you look at this, this is what we called g c before. Okay, so this is where you want to do that integration from -1 to 1 of g c dx. And you can clearly see, having j a function of c, it will increase the order of gc compared to f of x. Okay, so in this case, if j is a function of c, for instance, in the example that we just looked at, this was a quadratic polynomial, right? But if we use a mapping which looks like this, if it's a non-uniform mapping, the order of what we would integrate here is larger than quadratic. Sorry, the opposite. Yeah, this is larger than quadratic. Does that make sense? So here you would have maybe a polynomial of order 3, 4, 5, depending on what happens. We'll look into it. Okay. But what does that mean for you? That means you should not be fooled by just looking at the order of the integral that you had in the physical space. In this example, again, this is quadratic, but it doesn't mean that you need 2 Gauss points. You need to do the transformation. You need to calculate this. And based on the order of this one, you need to calculate the number of Gauss points. Okay, so this is the key. Does that make sense? Now, there are 2 implications about this. One is this thing that I just told you, it almost never happens in practice. So you do not have this information that I just told you. So basically your best guess is to go with the order of this one. So if that is quadratic, you usually can go quadratic. I mean, on the paper, we do one exercise together, but you don't have that, that insight to the problem usually. Okay, so that is step number 1. So let me maybe, based on what we just saw together, I think we established, or I think you are convinced now that we would like J to be uniform. Okay, J uniform is desirable. Does that make sense? Again, because we don't usually know what happens in between, but we know the order of the first function that we want to integrate, what is our best choice? I mean, we don't know what's going to happen here. So the best choice is to use a linear approximation or a uniform quadratic approximation such that you know J is constant. Okay, and then you know the order of G and F would be equal. Okay, so maybe remember, I call J constant, but I actually mean, sorry, I call it uniform, but I mean constant, obviously. So if J uniform is, or uniform mapping is desirable, that means J is constant. So that means order of F, F of X and G of C are the same. All right. So that is your, let's say, your friend. That is your best case, because I mean, we know that in practice this can happen, but the idea is to make it happen as least as possible. So that's the first message. So do uniform mapping as much as you can do. The second thing is we cannot do that either. So why? This is the question. Let's say we establish this. We like to have a uniform mapping. And I mean, in the picture that you have here, it looks so obvious to you that, okay, in order to have a uniform mapping, you need to distribute points equally. So what is so difficult about it? Does it make sense? So this is the second question. Why can we not distribute points equally? So maybe I just write it like that. Why is it so difficult? Or why is it not easy? Does that make sense? So the question is, or the assumption is, we want to have a uniform mapping. So let me just summarize this. So we want uniform mapping. Uniform mapping gives you constant J. That gives you identical orders for F and G. Otherwise, the order of G is always larger. Remember, G is always F times something, right? So this is the best thing. So you can imagine, let's say the order of G is always larger equal order of F of X. Okay, so the best thing you can do is to just make them equal order. If you could reduce the order, that would be even better, but you cannot obviously. So, but why is that so difficult? So that means, well, this is your physical space. I don't know, it is from, let's say, A to B. This is your natural space from -1 to 1, and then let's say the center point is here. So you would tell me all you have to do is to choose the third point to be exactly in the center. So why is it so difficult to do this? I think you cannot see it. Actually, it's not difficult at all in this case because it's 1D. If it's a one-dimensional problem, it's very difficult to see why it is difficult. But let me just draw a two-dimensional problem for you. If it's a two-dimensional problem, your natural space would look like a square, okay? So this would be your natural space. Now, this is your natural space. If it is 2D, now your physical space, if you are thinking of a two-dimensional problem, if it's a square, then you are lucky, of course. You can do the same thing. So this could be your physical space. So let's say this is your physical space. If it is like that, then you can construct a very nice constant J basically between the two. I mean, it would be like, let's say if this thing is 2 times larger, that J would look like 2002. It looks like a constant matrix if you want. But if your physical space looks like this, then there is nothing you can do about it. I mean, at best, you can just do this. But you can see that there is no way you can construct a constant mapping between the two. The mapping, because of the geometry, is not constant. Does that make sense? So long story short, the natural space is always uniform. Physical space is a function of the geometry. Okay, so your discretization of space would basically rule the rest of it. It's not always in your hand. So let me just come back to that slide, and I add this thing. So the thing or the problem or the key point here is that physical space is the result of, let's say, geometry of the problem. but also discretization. Okay, so again, you can think of more interesting examples. So if your space was something like circle, then there is no way you can make a nice mesh out of it using squares or triangles or anything. You know, you have to sacrifice something somewhere. All right, so this is sort of the message of why we do this example. Now we come back to the example itself and we just solve it quickly together. So this is the example. And as I said, we are going to just do that together. So let's do the analytical solution first. So for the analytical solution, we don't need any of this. So you simply integrate this thing. That would be just, let's say 2/3 x cubed plus 1/2 x squared minus x from 2 to 5. You insert those values and you end up with 85.5. Okay, so this is the analytical solution. Just keep that in mind for the next steps. Okay, so now we know the analytical solution is 85.5. Now what we want to do is to do this using first a linear approximation. So I'm going to remove what is not necessary. So we do this one, the transformation that you see down there. Okay, so in this case, remember what we did. You would want to change the coordinates. So you want to write x as a function of c, and you do that by just saying n1 x1 plus n2 x2, and n1 and n2, these are exactly what you have here. So you would have minus 1/2 c minus 1 plus times x1, and x1 is just 2 plus n2, which is 1/2 c plus 1 times x2, that is 5. If you calculate that, you get 1.5 c plus 3.5. Okay. Now this is exactly your x as a function of c, but it's basically a uniform mapping or a linear mapping. And as you can see, if I differentiate that, so dx would be 1.5 dc. Okay, so you get a constant Jacobian basically. Okay, as we promised. Now all you have to do is to do that integral, and for that I'm going to remove the quadratic one on the side. So based on the information you have, now you want to do the integral, and again, integral from 2 to 5 of what you have up there. All you have to do here is to insert this function. So here inside this, you should just say x equals 1.5 c plus 3.5. Okay, if you do that, you get a function which is integrated from -1 to 1, gc dc, and now that function is quadratic actually. because we know we didn't change the order due to the change of the coordinates. That's a quadratic polynomial. And we learned if you have a quadratic polynomial, the Gauss quadrature would tell you to just evaluate it with 2 points. And if you do that, you get also, let me just write it. You get 223, 264. I'm writing the numbers in case you actually do it and you want to check. And that would be exactly 85.5. Okay, so you get exactly the analytical solution. Okay, so that Gauss per element would be 2. Does that make sense? So that was the linear one. So we did the analytical solution, we did the linear solution. Now we want to do 2 quadratic ones. We will have a slightly longer lecture, so I will give you a break later. So I have not forgotten the break. It's just I want to finish this before the break, if you don't mind. So let's do the next thing. Now the next one is the quadratic one, but it's uniform. So we are going to do this. Okay, so this is the mapping that we are talking about. And as before, we just transform the coordinate x to c by using the summation, but now we have 3 points. So this would be n1 x1 plus n2 x2 plus n3 x3. Now this is very interesting because n1, it's a quadratic function. 1 over 2 c minus 1 times coordinate of point 1, that is 2, plus n2 is 1 minus c times 1 plus c times 3.5 plus n3 is 1/2 of c times c minus 1, sorry, c plus 1 times 5. Okay, let me also remove the linear one so that you are not confused with this. Okay, so we took these shape functions, obviously. So what do you think you will get from this? If you just simplify that, not very surprisingly, you get 1.5c plus 3.5. So remember, we did a quadratic approximation. We used everything quadratic, but because the mapping is uniform, you get exactly the same uniform mapping as before. So that quadratic term automatically disappears because there is nothing quadratic about this mapping. The Jacobian is constant, okay? So you end up with a constant Jacobian again. So that tells you dx would be again j dxc. And basically doing this, it brings you exactly to the same integral that you had before. Okay, so if you insert that here, x is 1.5 c plus 3.5, and dx is 1.5 dxc. If you do that, again, you end up with an integral over c from -1 to 1, which is a quadratic polynomial. And sorry, yeah, it's a g. And inside the g, you have already the j part. Yes, so this is a quadratic polynomial again. And then again, you also need 2 points like before, and this also gives you exactly 85.5. Okay, so equal to the analytical solution. Does that make sense? All right. The last thing I want to do is to look into this example, but now we do it using the quadratic non-uniform version of it. So if it is quadratic non-uniform version, that means instead of, so the point in the middle is not exactly in the middle, we put it at 4. Okay, so it's slightly towards right. And let me just put this up here. Yeah. Okay, so this is what we have now. Again, the process of writing x coordinate is the same as we did before. X is n1, x1 plus n2, x2 plus n3, x3. Now, n1, n2, x, n3, we just take it from what we have on the corner. So again, 1/2 c minus 1 times 2, coordinate of point 1, plus 1 minus c times 1 plus c times 4 plus the last coordinate is 5. It's multiplied by n3. Now, if you use this one and you simplify that, you get minus 1/2. Let me write it as minus 0.5 for simplicity. So it's minus 0.5 c squared plus 1.5 c plus 4. Okay, so now your mapping is no longer a linear mapping. It's not a uniform mapping. What I call uniform previously in terms of mapping is a linear. So that means the Jacobian of that is not constant. So dx would be minus c plus 1/2. Okay, times dc, or in other words, j is simply minus c plus 1.5. Which tells you what? It tells you if c was 0, Jacobian is 1.5 like we had before. But for every other point that is not exactly in the center, that is not true, which also makes sense. So it tells you the right-hand side basically is, I mean, it has more contraction on the right, it has more extension on the left. But at the center is 1.5, let's say, and then it changes from right to left. Okay, so this is really what you need to do. And now it is very easy. The next step is very simple for you. All you have to do is to use that into, so to use this quadratic x, which is minus 0.5 c squared plus 1.5 c plus 4. So that is your quadratic x, and then your dx. So here you use the x, and then you also change the dx to minus c plus 1.5 dc. Now, if you do that, your integral would be something from minus 1 to 1 gc dc. But this integral for now, it would be an integral of order 5. Okay, so you would see it here. See, now your x itself is a quadratic function. So it comes here. So a quadratic function to the power 2, that would be 4. Okay, but also you have this dx, which is another function. So you get this polynomial of order 5, basically. And then because it's a polynomial of order 5, then you need to see how many points you need for a polynomial of order 5, and we can come back here and we cheat, let's say, from our table. So for a polynomial of order 5, you need 3 Gauss points. Okay, so you do 3 Gauss points and you calculate that. So if you do that using 3 Gauss points, you also get, of course, the correct answer. Okay, but if you were not careful about this, if you did this using 2 Gauss points, you would get an answer which looks like 84.834. Not too bad, not too bad. I mean, it's not a horrible approximation, but now you see you lost the exactness of the solution. Okay, so this is important that this 2 Gauss point is nice. So again, that is the message of this exercise. If you look at the function, it's quadratic. So it reminds you of 2 Gauss points. And as I mentioned, you don't know better. So if you know the function is quadratic, you usually think of 2 Gauss points. But then in order to make those 2 Gauss points perfect, or as perfect as they can be, the trick is to make sure that your approximation or the spacing is as uniform as possible. Okay, so that is the idea. Okay, and then again, if you do finite element discretization, there is always this step about discretization, about meshing. And there is this thing called structured mesh. And if you use something like Abacus or COMSOL or something like that, they have also these features to test the efficiency of the mesh. So what I'm trying to say is that, I don't know, if you have an element like this, try to mesh it like that. Okay, if instead of doing that, you mesh the same thing like this, you introduce an error into your solution, into your finite element solution. A uniform mesh is always better than a non-uniform mesh. Okay, from also other aspects, but I just mention it from let's say integration viewpoint. It's always nice to have a uniform mesh because then it ensures a uniform mapping. Let me just do one more example and then I give you a nice break. Okay, so the second example is actually pretty short. I just give it to you in case you want to test your calculations. So let's say you have an integral from 2 to 5 x cubed plus x squared dx. The analytical solution for this would be x4 divided by 4 plus x3 divided by 3, let's say from 2 to 5, which gives you 191.25. So that's the analytical solution. And now we want to do the approximate solution using linear approximation. And for that, I'm going to actually, again, go back to our slide here, and I copy the linear shape functions. So these are the linear shape functions that we are going to use next. So here you would write, again, x as a function of c. That would be n1 x1 plus n2 x2, which would be, in this case, minus 1 over 2 c minus 1 times x1 is 2. You see, it's from 2 to 5, so x1 is 2, x2 is 5, plus 1 over 2 c plus 1 times 5. So if you do that, your x as a function of c would be simply 1.5 c plus 3.5 again, that means dx is simply 1.5 dx, or otherwise j is a constant of 1.5. So all you have to do is, again, the same thing. If you include this x into your integral, so let me just do that. So now that we know this is the x, let's just include this x into that integral and also include j into, into that. So this would be j dx, and then here you replace the x by the function you have. So you end up with this integral from 2 to 5, from -1 to 1 now, which looks like just 1.5 c plus 3.5 to the power 3 plus 1.5 c plus 3.5 squared, and all of that times 1.5 dx. Now, you may be tempted to expand these terms, but you don't have to, right? You know it is a cubic function. You need 2 Gauss points to calculate that. So all you have to do is, again, just call this thing all together, let's say gc. This integral, all of it, is going to be g at -1 over square root of 3 plus g at 1 over square root of 3. Okay. And then again, it's cubic polynomial. That tells you Gauss per element is 2. And that gives you also, again, let me just write it for you in case you want to test it. 37.818 is for the first term, and 15343 is for the second term. And if you add them up, you also get 19125, which is the exact solution again. Okay, so this was just another example how this numerical integration works for us. All right, so this was the end of one-dimensional finite elements method. What we want to do next is to have a short overview and wrap up of everything that we have done, let's say, so far from the beginning of the semester.